Let's talk about the array implementation.
Right. Since a stack is linear, an array seems like a natural fit. You can store items one after another in array slots.
But an array lets you access any element, right? How do you make it act like a stack?
That's the key constraint. You must restrict yourself. Even though the array allows access anywhere for it to be a stack, you only perform insertions, push and deletions, pop at one end, the end we designate as the top.
And that's where our top variable comes in again to keep track of that end.
Exactly. In an array implementation, pop is usually an integer index. It tells us the index of the last item inserted.
How do we start? With an empty stack.
Conventionally, we initialize top to MACD1. This indicates that the stack is empty. There's no valid element at index MACD1.
So top being 0 means there's actually one element in the stack at index 0.
Precisely. Top points to the index of the topmost element.
Okay, so let's push. How does that work with the array and the top index?
2 steps, basically. First, you increment top. If it was -1, it becomes 0. If it was 0, it becomes 1, and so on. This moves the top marker to the next available slot.
Okay, make space at the top.
Then you store the new data item in the array at that new top index. So stack our top equals data.
And if we keep pushing, top keeps increasing, and we fill the array from index 0 upwards.
Yep, push 10, top becomes 0, stacker 0 gets 10, push 20, top becomes 1, stacker 1 gets 20.
Until we hit the end of the array, what happens then?
That's our stack overflow condition in the array context. Arrays have a fixed size. If top reaches the last valid index, say max size 1, and you try to increment top again for another push,
there's no stacker top to put the data into.
Overflow.
Exactly, you've run out of allocated space.
Okay, that's pushing. Now, how about pop with an array? Do we, erase the data? Not usually. It's much simpler. To pop, you typically first retrieve the value at the current top index, so you can return it if needed. Then you just decrement the top index by 1.
Decrement top, so you just move the marker back.
Yeah. If top was pointing to index 3, after popping, it points to index 2. The value at index 3 is still technically there in the array's memory.
But the stack doesn't consider it part of itself anymore, because top says the stack ends at index 2 now.
Exactly. It's conceptually removed from the stack. Future pushes might overwrite it, but as far as the stack operations are concerned, it's gone.
That's sufficient. No need to actually clear the memory. Okay, the notes have some CC++ code snippets for push. What's the first one, Show?
Activity 1, yeah. It's a very basic push. It just increments top plus my top and then assigns the data to stack army top.
Simple.
Well, what's missing?
There's no check for overflow. If my top is already at the maximum index, max1, where max is 4 here, incrementing it goes out of bounds. The code might crash or just write over other memory, which is bad. The output just shows 4 successful pushes. Not ideal. What about the second push snippet, activity 2?
This one's better. See the if statement at the beginning. If top in equals 1.
Right, it checks if top is at the last valid position.
Yeah. If it is, it prints stack overflow and just returns, preventing the invalid push. Much safer.
And the output shows that. It pushes 4 items fine, but the 5th attempt triggers the stack overflow message.
Exactly. Which leads to that question in the notes. How do we overcome stack overflow?
Well, maybe use something that isn't fixed size, like not an array. Or maybe make the array bigger if it gets full.
Those are the main ideas, yes.
Yeah.
Using dynamic structures like linked lists or techniques like dynamic array resizing, good thinking.
Okay, let's look at the pop code. Activity 1 first.
This pop function first grabs the value from stack or pop and stores it in a temporary variable value.
Okay, saves the top value.
Then it decrements top 1.
Move the marker back.
And finally, it returns the saved value. So it gives you back the element while also effectively removing it from the stack's view.
But again, what if the stack was already empty when we called this?
Big problem. If top was madish1 initially, trying to access stack R1 is invalid. That's where activity 2 for pop comes in.
Let me guess. It adds a check.
You got it, right at the start. If top natus1
checks for the empty condition.
Yep. If it's empty, it prints stack underflow. And in this example, it actually calls exit, which stops the whole program. A bit drastic, maybe, but it prevents the error.
And the output reflects that. After popping all items, the next pop triggers the underflow message.
So these checks, overflow on push, underflow on pop, are absolutely essential for robust stack implementations, especially with arrays.
Definitely seems that way. Okay, let's circle back to applications. A maze example.
Imagine you're at an intersection in the maze. You have, say, 3 possible corridors to try. You pick one. Before you go down it, you push your current location, the intersection, and maybe which path you chose onto the stack.
Okay, saving my state.
Right. Now you explore down that corridor. If it leads to the exit, great. If it
Okay.
leads to a dead end,
I need to go back.
exactly. So you pop from the stack. This restores your previous state. You're back at the intersection. Now you know not to try that first corridor again. So you pick one of the other unexplored options, push your state again, and continue.
Ah, so the stack acts like a breadcrumb trail of decisions, letting you undo the last choice and try another.
Perfectly put. It manages the exploration history, allowing you to systematically backtrack when needed. Same idea applies to finding paths in graphs or exploring moves in games.
That's really powerful. Okay, and the other really big one was function calls. How does the stack